Welcome back to the last lecture in the Logistic Regression series, that is Logistic Regression Part 3. And in this part, we assume that you have cleared all the theoretical foundations by watching the video of Logistic Regression Part 1 and Logistic Regression Part 2. Over here, we will take an example how to solve our logistic regression, how to apply logistic regression. So you see, we have taken a sample data set where we have the hours of study. The students are students are studying for 1 hour, 2 hour, 3 hour, 4 hour, 5, 6 and 7. And what is the outcome of their study? If they studied for 1 hour, the student actually fails. For 2 hours study per day, student fails, and 3 hours study per day is fails, or the student fails. But if a student studies for 4 hours in a day, it passes. For 5 hours in a day, it passes. For 6 it passes, and 7 it passes. We have taken a sample, very small sample, just to show you that how logistic regressions are actually calculated, how the calculations are. So you can note down this on a piece of paper separately, because the data will be used throughout the lecture. Okay. So this is a sample data set. Now, the first step is we will define the sigmoid function. You are calculating the probability of a student, okay, when a student passes. Okay, what is the condition? How many hours, minimum of number of hours that user inputs, and you can find out whether the student passes or fails. Okay. So we have a logistic regression which is using sigmoid function, and we are calculating for pass. If we are calculating, if this would have been y equals to 0, then we are actually doing it for cases where the student have failed. So we need to find the probability of y, that is the student passes, on the entire data set of x, provided that our sigmoid function is 1 upon 1 plus e to the power w x plus b. And remember, in data set we have only study hours. So that is the one input feature. Okay. So the equation of line, if you simplify that, so we have y equals to mx plus b, because we need a line. Okay. So that equation is actually inserted over here. Now our task is to train this logistic regression and find the value of w and b, where mostly it predicts the behavior given in the data set. So x is the hours of study, y is the outcome, pass or blink fail, w is the weight to be learned, and b is the bias to be learned. So we have to actually calculate w and b, and once we can do that, that means we have trained the logistic regression. Okay. So we have initial parameters, because at the beginning we don't know the weights, so we start with w equals to 0 and b equals to 0. Okay. Now at step 3, what we'll do, we'll substitute the values from the data set by w and b, and what we get, since whatever value you initiate in this equation, okay, since w equals to 0 and b also equals to 0, so this product becomes 0 multiplied by x plus 0. So finally, for the first time, it evaluates to 0. So e to the power 0 is what? It is 1. So this entire expression evaluates to 1. So that is 1.5 is the predicted probability in the first iteration, and that is 0.5. It is 50-50. Okay. So the initial prediction for all x, the initial prediction is 0.5. Now the next step is to calculate the log loss. Okay, so that is yi log yi 1 minus yi multiplied by log of 1 minus yi, and over here the number of samples in our data set is 7. The value of data set is 7, the number of records you can say. And we have already calculated the predicted probability, that is 0.5. Okay. So yi can be calculated, no issues, but over here we can use some mathematical tricks, because since this factor log 0.5 is common to both the sides, so what we can do, we can take it out common inside the summation mark. So log 0.5 has been taken out. Now that what remains in the square bracket is y plus 1 minus y. It remains. So y get cancels, and summation of log of 0.5 multiplied by 1. So it's a constant, log 0.57 is constant. So we can do is we can take it common. So that is log of 0.5, and the summation remains, and we have to sum it from I equals to 1 to I equals to 7 for every output. So this evaluates to summation from I equals to 1 to m is 7, evaluates to 7. Okay. So that is minus log of 0.5 divided by 7 multiplied by 7. So that strikes out. So we are only left with 0.693 for the first time. Clear? So this is our initial cost, 0.693. Now we'll move to another point. So what we have to do, now we have to actually update the weights. We have to update the weights. So what we will do, use the gradient descent, and we will have to take the partial derivative of del of j divided by del of w. And yi is actually the predicted probability minus the actual. Actual is given in the data set, you can remember. For 1 hour, 2 hour, 3 hour, the student fails. The student start passing the exam when he studies 4 hours daily or above. Okay? And similarly, we can do a partial differentiation of this entire thing to find the weights bias B. So we can put this equation into play, and yi cap we have calculated, the predicted probability have been calculated. Now y is to be used from the data set. So we'll expand this. So you remember the data set? It says 0.5 minus 0. That's the first value of available from our data set. The output is 0 when the student studies for 1 hour. 0.5 minus output 0 when the student studies for 2 hours. Output is 0 and the student studies for 3 hours, and output is 1, that is student passes when he studies for 4 hours, 5 hours, 6 hours and 7 hours. So if you do the calculations, so it all sums up to 1 upon 7 divided by minus 8, and it becomes minus 1.14. Similarly, when you do partial differentiation of B, so over here you don't use the x, the rest expression remains the same. There is no multiplication factor of x. So you see for the first case, output is 0, 0, 0. For 4 hour, passes, student passes, and when the student is passing, so we use 1. So that calculates to 0.07. Now this is what we have found, the partial weight. Now let us assume the learning rate and fix we improve the weights. So that is, earlier we have used the weights W equals to 0 and B equals to bias is equal to 0. So when we do that, so this factor was actually 0, okay, and this bias is also 0. That we have used as a random guess. We started with 0. Or you can use any value, but and apply gradient descent, it will automatically correct. So alpha, the learning rate is assumed to be 0.1. So this is the log loss partial differentiation which we calculated previously. It was minus 1.17, it is 0.07. So 0 minus 1.1, that's the learning rate multiplied by this factor. So what it does, at it just converts the negative values to the positive values divided by 10, because it is multiplied by the factor of 0.1. So the new parameters that we have learned from the first iteration of data set is 0.114, that's the weight value of W, and B bias is 0.007. Okay. Now what we'll do? We are at the step 7. We have to actually iterate this many times, unless and until the algorithm converges. Now let me give you a recap. Okay, on the iteration 2. So for the first iteration we have calculated these values. Okay, now what we'll do? These values have been calculated. Now earlier we were using W as 0 and B as 0. Now we will use these weights and we'll find out the new predicted value for the iteration, second iteration. So X was given, the number of study hours, the original output was given, and now for the second iteration you are calculating the output. So let's find out what is the new output. So putting that thing into the equation, the linear function Wx plus B evaluates to 0.21, 0.235, okay, and so on. And whenever you are solving a logistic regression problem or you are doing the computations, always use tables. Okay, so that actually summarizes everything over the place rather than scattering throughout the copies. Okay, so now this value, now this value 0.121 is used into the sigmoid function and we get the new values. Now we are using and we are repeating the same calculations for all the values. Remember that this is 1 hour study, 2 hour study, 3, 4, 5, 6 and 7, and between this the student is actually passing the exam, and this set the student is actually failing in the exam. Okay, so you see that after in the second iteration the values of 0.5, 0.5, 0.5, okay, they are being in the range of 0.5, and wherever the student is passing, the first digit is actually 1.1 greater than the other case. Now this is the effect of gradient descent and on the predicted output. Now when we iterate for the third time, then these values will be further refined, and if you keep on repeating the step, ultimately this will be settled to 0 and these will settle to 1, and once it is done, our algorithm has been perfectly trained. It has learned the data set, the input features have been correctly learned. then you can give unforeseen data and it will do the predictions for you. And for that you will have the accurate value of W and accurate value of good value of B also, bias. So this is the sigmoid output of Y. Now for the iteration 2, now we have to calculate the partial derivative of del of J divided by del of W, and similarly we have to calculate the partial derivative of log loss with respect to bias B. Now what we'll do, you have this new value calculated which you calculated in the previous slide. Now that will be used for each output. This is whatever have been underlined is predicted. It is predicted. It is predicted by your algorithm. Okay. So ultimately you find the weight to be minus 0.588. So this is the, you have calculated del of J by del of W. Okay. Now we will do for bias also the similar calculations, and now the bias comes to 0.041. When we are calculating the bias, we are not multiplying the input x. Okay. So in the second iteration, what we'll do, we will update the weights. So previously what we are using, we are using the value of 0.114 and the bias we are using 0.007. Now we have this partial differentiation value for weight and bias respectively. Doing the calculation, putting into the equation, that is 0.172 and this is become 0.003. So these are the two values for two parameters for an equation of straight line. Now this you have got after second iteration. Now you have to iterate for third. Okay. Unless you keep on doing the iteration unless and until the log loss function stabilizes. That is, there are no more changes in log loss function. Okay. So you have to repeat. And after sufficient repetition or when the log loss function stabilizes, you are sure you can stop this iterating process and you can find the proper, you will get the proper weights and bias. So you see that we started from 1.14 and 0.057. Then we have 0.12, 0.03, and slowly the W stabilizes, weight bias starts from positive, goes to slightly negative, and then it starts its values. Okay. So when we stopping criteria, the stopping criteria is when WB converts to optimal values, the cost function is stop decreasing significantly. You see that the cost is decreasing at every step. Okay. So there would be hardly no changes in the cost. So that becomes the stopping criteria. Okay. It is not possible to show the complete iterations, but this after 7 or 8 iterations, okay, you have this value. And you can practice it at your home. Okay, and you can get the stable values of J. And when you get the stable values of J, you can stop. So at that point, you have trained the logistic regression model. Now in that model, now you give unforeseen data, it will do the correct predictions. So that's an end of our lecture 3. Okay, hope you understood. Thank you.